Loon is, we're now on the site of UC Solar looking at Descp2 collection tubes, and Loon will explain the uniqueness of the Descp2 versus the ICPC.
Okay. So this is Descp2. The major characteristic about this is that it has a non-imaging optics formed external reflector. So that's why it's called Descp2 compared to ICPC. The reflector itself is made out of aluminum sheet metal. So you can see it's a little bit flimsy. Coated with a sticky vacuum deposited high reflection film. It's about 89% reflectivity, hemispherical. The shape is faced, you can see the aperture is actually faced directly to the local latitude. So actually you are tracking in a way the seasonal change of the sun here, and it's sitting still. It's not supposed to be tracking, but the sun moving within this area, moving within our seasonal change, will always be focused. The light will be always focused onto our absorber here. The absorber tube is made out of 100mm borosilicate evacuate tube, and the absorber itself is inside, and it's a particular Germany produced absorber selective coating. The coating is on 0.12mm thick copper sheet metal, and the absorber shape, the cross section of the absorber is actually a pentagon shape. It's control bent, so it retains the shape very well. And our optical design, because our specialty is in optical design, so we actually have the perfect optical design to match with this particular shape. There are within the evacuate tubes, you have an inlet, you have an outlet, and it's basically two copper tubes. Each copper tube is 8mm thick diameter, and within the copper tube we flow the mineral oil, the Durotherm 600 mineral oil. And the advantage of this particular model here is because of the higher concentration ratio, which is about 1.4 times pi, compared to a traditional all-glass vacuum tube. It can reach higher temperature, where we have tested this to be at about 45% at 230 degrees Celsius, under a room temperature of about 11-12 degrees Celsius. So this particular model can really heat up well, even during a very, very cold weather. So the manifold box here is in between, and it's having a parallel flow between the two wings. And for each three tubes here, we have the each tube connected with each other in a series connection here. And there are radiator clamps here to secure the position, and also to make sure it's staying at the right focus for the optics. The rubber gasket here is serving as a protective purpose, and also as a little bit insulation here. And I can open this up again. This is our metal glass vacuum tube. So you can see there is a metal pole bar, there's a glass flat surface, and it's thermal compression fitting these two together. And this kind of seal can last over 25 years, and we will not have a problem with the vacuum. And you can also see there are two gas scatters, two evaporated barium gas scatters, one on the top and one on the bottom. And we also have, you can't see inside it, but there are another 3 long-term barium gathers, just to make sure that this vacuum tube will be maintaining its vacuum over a long time, regardless of the outgassing from either the metal or the mineral oil, which has small hydrogen atoms going through. The reflector here, as shown, is done by 2 pieces for each tube. That's just our current manufacturing limitation. In the future, we can bend it as a whole reflector. And on the back, all these ribs are shaped according to our optics. They're actually water jet cut. It's a very cheap process, and they are made from 0.6 millimeter aluminum sheet metal, and we cut them in decks. And also the different bars here are just there to secure the structure of the whole collector and also support the ribs. And again, because of the metallic absorber and metallic heat transfer channel here, we will not have any problems with either pressure or thermal shock. So the whole collector is specifically designed for robust industrial applications.
How long has this installation been here being tested?
This installation has been here for about a year, and we have had experience with it in connection with our absorption chiller there. So that chiller, that box here is a absorption chiller, double effect absorption chiller using lithium bromide as the fluid. The high temperature generator inside of the chiller is 150 degrees Celsius, and we power that chiller with 180 degrees Celsius hot oil. So it has to be a little bit higher temperature to allow heat exchanger to work. The whole array here for this front row here is 50 square meter. There are 45 square meter. There are 10 modules. Each module is 4.5 square meter for the aperture area. And we have the previous generation on the second row also.
Has there been different generations of the evacuated tubes, tested here, or is this?
Yes. Yes. We have had many generations actually. So starting with the further away part, we had the first time was 65 millimeter single module being tested. Then we move on to the back row here, which is 65 millimeter multiple of them. You can see there are 50 square meter there. And then we move on to this particular model here, which is first tested also as single module and then as multiple modules as this little array here, demonstration as a demonstration product. Yeah.
Right. Well, thank you very much for the explanation. Have there been other evacuated tubes that would have been similar to this that you've seen, that you've tested, or is this a very unique design in its own right?
Well, the other evacuated tubes, particularly with our optics we have tested, is also the all-glass evacuated tubes. So we had different heat transfer designs for that, including the counterflow design, including flowing the oil directly into the tube, and also having aluminum fin copper tube design, aluminum fin heat pipe design. All those do not stand up to our product here simply because of heat transfer reasons. In all glass tube, you have for optical design you have to have a bigger gap loss, and for heat transfer design you are faced with the insurmountable challenge of how to take the heat from the glass into your fluid. And
what
that
type
is
of,
not efficient.
What type of fluids do you find to be the most, I guess the extreme fluids where you have water, antifreeze, and then specialty fluids? How do you choose the different fluids?
We choose our fluid based on the temperature that we work with. Generally, anything below 150 degrees Celsius, that's about 10 atmosphere of pressure. So below that point, you can really work with water plus antifreeze. The heat transfer of water is exceptionally good. It's most common resource you have on Earth, and it's just really good at heat transfer. So you use that. Anything beyond 150 degrees Celsius, in particular cases when we have to deal with stagnation, the mineral oil actually serves for a better heat transfer fluid, simply because it's going to be kept at room temperature, room pressure, so it's very easy to handle that pressure. And also the property of the mineral oil generally goes to up to 300 degrees Celsius.
And do you need particular pumps for water versus the oil, or
Yes.
can these be pumpless?
Yes, well, you do need, in both cases, you need pumps, at least for the whole array. For single collectors, heat pipes by itself can warm up, but you still need some kind of pump to push the working fluid through the system. And for between water and oil, generally for oil, you want to pick a special pump.
Have you given any thought to the storage of the heat? Have you worked on that here, or have you only seen that occur, in our sites in Mongolia?
Well, the storage actually is our advantage here because we are allowed to go to higher temperature, and in order to store the heat, you do need a little bit temperature difference between your array and your working temperature, your load temperature. For our particular case here, we are not using any hot storage. We are simply storing the cold water coming from the absorption chiller, but we can of course envision that in other places like in Mongolia, you can use hot storage.
Mm-hmm. Well, thank you very much for your explanation for the XCPC, and we'll look forward to the new innovations in the future. Thank you.
Thank you.
I guess there we go.